Okay, so we want to take a look at a new method for solving a system of linear equations. It involves something known as the LU decomposition. Now, decomposition is essentially a factoring, if you will. It's a way of taking a matrix and breaking it down into a product of two or more matrices. And this is a big thing in linear algebra. There are many other types of processes or times when that is a useful thing to do. Okay, this is described in the textbook in section 9.1 actually, so you can look there. This is what I'm going to do, essentially covered in there explicitly the same way. LU, let's talk about that, a factorization of a square. So we're going to be talking about a square matrix. So this will be restricted in terms of where we can apply this process, and we'll explain that. But for a square matrix A, we want to factor it as L times U, where L is an n by n lower triangular matrix and U is an n by n upper triangular matrix. So that's an LU decomposition or LU factorization of A. So now you know why I call it LU, right? L for lower, U for upper. Okay, so before we actually show how do we obtain that LU factorization, that's a process in and of itself. We want to show you how does this have to do with solving a system of linear equations. Okay, so let's start out with the steps real quick here. We want to solve the system AX equal B, right? A is an n by n matrix again. So A is our coefficient matrix. So notice that this method for solving will only work when you have the same number of equations as unknowns, right? When your coefficient matrix A is indeed square, n by n. X, of course, is the unknowns. That's what we're looking for, x of 1 through x of n. And B is our corresponding constants, right? N by 1 vector. All right, so here's what we're going to do. We're going to rewrite the system AX equal B as LU x equal B. So we're going to write A and just replace it with its LU factorization, okay? And now what I'm going to do is this. I'm going to look at the product UX. Remember, UX, U is n by n, x is n by 1, so UX is n by 1. And so that's going to be equal to some other n by 1 vector. I'm going to call that Y. I'm going to define this new matrix Y by UX equals Y. This gives me a new system of equations, if you think about it, where the coefficient matrix is now this upper triangular matrix. And X is the unknowns. Y, of course, is sort of a placeholder. Now, what is Y? Well, if I go back in and replace UX here, right, with Y, I'll get what? LY equals B. And that's what we get this system LY equals B. Right? So now B, these are known, these are constants. L will have that lower triangular matrix, and Y will now be a different set of unknowns, okay? And so we can solve this system, right, for Y. Once I've solved this system for Y, I can go back to this system, UX equal Y. Since I know what Y is now, I can solve for X, right, in that system. Now, let's think about this. Isn't that great? Let's see what we've done here. We started with one equation, right, and solving for this system of equations, and I've changed that problem into solving this equation here in step 3, system of equations, and then this system of equations. Ah, isn't that lovely? We started with one system of equations, and now we have to solve 2. Wait a minute. That seems complicated. Why did I just make more? Well, let's be careful here. Solving these two systems is not going to be any work at all if you think about it. In fact, if you think about this second one here that we saw, this upper triangular one, right? If you think about upper triangular matrix, any matrix that's in row echelon form is going to be upper triangular. And you'll notice that this system will be easy to solve by simply using back substitution. There won't be really any row operations to do. So we just do back substitution. And then this one here, this first one we have to solve, it's actually going to be something called forward substitution. Okay? So even though we've got 2 new systems to solve, they're going to be easy to solve. Okay? So you say, where's the process? The process, of course, will be in finding the LU decomposition. That will be a little bit bogged down, and we'll talk about that here in a moment. So let's look at this system. Matrix A, or let's look at this matrix first of all, is 3 by 3. It can be shown to have the following LU decomposition. Okay, so if you multiply L times U, you're going to get the matrix A. Okay, notice L is a lower triangle. Remember what that means. Entries above the main diagonal are 0. Upper triangular entries below the main diagonal are 0. Okay, so L times U. So here's a LU factorization for the matrix A. Okay, so now what we want to do is solve the corresponding system, AX equal B, where A is this coefficient matrix, X is our unknowns again, and B now, these are our constants. So notice the first equation would have been what? 2x1 plus 6x2 plus 2x3 equals 2. Second equation, negative 3x1, negative 8x2 plus 0 equals 2, and so on. So we've got three equations, three unknowns. All right, so remember the process. We're going to start with AX equal B, and we're going to replace A with LU, right, which is this. So I'll have this system, LU, X equal B, and then we're going to call UX, remember, U is n by n, X is n by 1, so this product right in here is n by 1. I'm going to call that a new variable called Y, okay? And that gives me this system here. All right, we define Y to be the vector with Y1, Y2, Y3. We don't know what those are, but we get this new system, UX equal Y, okay? Now UX equal Y, if I replace L or UX with Y, I get LY equals B, LY equals B. And that's the system here, LY equals B. And this is the system I want to solve first. Okay, this is the system I want to solve first. And if you think about it, I can do that. B is known, L here it is. And look at this. This is actually solved by forward substitution. If you look at the first equation, what's it say? 2y1 equals 2. Okay. I mean, I could put this matrix in reduced echelon form, but why? I don't want to do that, right? That would be a nightmare. I can see clearly from this first equation that y1 is equal to 1, right, dividing both sides by 2. And then the second equation, notice I got just y1 and y2. I can replace that. I know y1 is 1 in here, right, and solve for y2. And then once I have y1 and y2, the last equation, notice, I'm going to plug in for y1 and y2 to get y3. So this is called forward substitution. Right? So I plug in, I'm going to get y1 is 1, as we said, y2 would be 5, and y3 would be 2. So I can get this values for this sort of intermediate variables I've introduced, this intermediate variable y. Okay. Once we have that, we go back to the ux equal y. I now know what y is. I can now solve for x, which was my original problem. So I go back to this equation, ux equal y. My y1, y2, y3 are now my constants here, and I solve this system. And notice this system, if I write out the system equation, this is just a simple back substitution, right? Notice x of 3 is 2. Plug in x of 3 is 2 here. I get x of 2 is negative 1. Plug in negative 1 for x of 2. 2 for x of 3. I'll get x1 is 2. And this is the actual solution we were looking for the original system. And we can check and confirm that. Okay. So that is the way we use an LU factorization to solve the system. And you can see that's pretty easy. Really, you say, wow, there's nothing to it. It's just a forward substitution and a back substitution. Okay. But there is some cost, and that is finding this LU factorization. So let's talk about that a little bit. The person who kind of popularized the use of this factorization technique was Alan Turing. Some of you are familiar with him. He was a mathematician who was instrumental in breaking the Nazis' Enigma code during World War II. Some of you might have seen the movie The Imitation Game. It was in 2014 with Benedict Cumberbatch, is that his name? Pretty good movie there. At any rate, how do we find this LU decomposition? Well, we have this theorem I want to just look at. We're not going to prove it, but if A is a square matrix and it can be reduced to row echelon form, U, and notice any row echelon form is going to be upper triangular, okay? And using Gaussian elimination without row interchanges. I don't have to do any row interchanges. If I can reduce it to a row echelon form without row interchanges, in other words, just multiplying one row by a non-zero constant, adding a multiple of one row to another, if I only go do those two operations, then A can be factored into an LU decomposition. Okay, and so if that's the case, so not always do we have an LU decomposition. It turns out, we'll see later on, that if we have to do a row interchange, you can have something called a PLU decomposition, a little bit different. P is what we call permutations matrix to handle those row interchanges. Okay, but if we can do that, if we can reduce A to its row echelon form here, not necessarily reduced, just row echelon form, and we're going to do that by multiplying A by its corresponding elementary matrices. Remember, elementary matrices, if we multiply on the left, they will perform that corresponding row operation. Elementary matrices, remember, obtained from the identity matrix by doing one row operation. And whatever that row operation is, when you multiply E1 times A, it will perform that row operation, and the product will be that operation done to the matrix A. So, E1, I get my, whatever I have to do, row operation wise first, E1, and then E2 all the way to EK. So there's a sequence of row operations that we do. Again, no row interchanges. Okay. Since elementary matrices are invertible, if you remember, we can multiply by their inverses successively out here. EK inverse first. So I'm going to multiply U by EK inverse, and the EK inverse times EK would be the identity, and then EK minus 1 inverse, all the way down to E2 inverse, and lastly E1 inverse. So I'm solving for A. All right, remember the order matters. I have to multiply on the left here. Okay, so I solve for A. And it turns out here's the key, if no row interchanges have been performed, right, then all these inverses here turn out to be all lower triangular. And if you remember, a product of lower triangular matrices is lower triangular. So these inverses multiplied together, that becomes a lower triangular matrix. This is upper triangular, and we get the decomposition. That's sort of the way it works. So, for instance, if I wanted to find the LU decomposition of this matrix here, okay, then we think about, can I do it without row interchanges? Well, that's important. So I don't want to use any row interchanges. So what I have to do is look at this first entry. I want it to be a 1. That's what I'm going to do, put it in row echelon form, so I want a 1 here. So if I have a 1 down here below, I don't want to interchange, right? You don't want to interchange rows. So you got to multiply by the reciprocal. The reciprocal is half times 2, which gives me 1 there. There's my leading 1. Now, I want to keep track. The corresponding elementary matrix that I would multiply by, E1, would be the identity matrix with row 1 multiplied by half. There it is. Right? What's the inverse of this matrix? It's also elementary. The inverse of multiplying row 1 by half is to multiply row 1 by 2. Right? If I want to get back to the identity matrix, I need to multiply row 1 by 2. Here's the corresponding inverse matrix. I want to keep track of those, right? Because the idea is that the product of those matrices is lower triangular. Okay. Next, I want to get zeros beneath my leading 1. So I need to get a 0 here. How do I do that? I add a multiple of one row to another. I take row 2 and add 3 times row 1 to it. That will zero that out. Okay. What's the corresponding elementary matrix? So if I add 3 times row 1 and add it to row 2 of the identity matrix, I get this. Right? How do you undo that? What's the inverse? Well, here I added 3 times row 1 to row 2. Now I need to take negative 3 times row 1 and add it to row 2 to get back, right? So I add 3 times row 1 to row 2. I want to sort of subtract 3 times row 1 to row 2 to undo it. And so here is the inverse matrix for that process. Okay. Then to get the 0 here, I'm going to do what? Row 3 plus negative 4 times row 1. That gives me the 0 there. Here's the elementary matrix used to do that. Here's the corresponding inverse matrix. Okay. Now, in this case, I've got a 1 now, and I've got this locked in place. So I don't want to mess with that. Now I go to the second row. I want to get my next leading 1. Well, I have it right there. So technically, I do nothing. Okay. You could say you can multiply row 2 by 1. The reciprocal of 1 is 1. So if you're writing your algorithm, you actually might have that happen. But we won't do that step here because then the elementary matrix is just the identity matrix, and the inverse would be the identity matrix. So then I have the leading 1 already. I want to get a 0 beneath it. How do I do that? I take row 3 and take 3 times the pivot row, which is row 2, right? That's going to zero out that entry beneath that leading 1. Here's the matrix, elementary matrix that does that, right? Doing 3 times row 2 added to row 3 of the identity matrix. And this is the inverse matrix for that elementary matrix. Lastly, I need to get a 1 here. Multiply row 3 by 1/7. The reciprocal of that is 1/7. So here's the elementary matrix. Here's its inverse. Okay. Notice we are in now row echelon form. We're going to let that be our U. Okay, it's upper triangular. Notice only zeros below the main diagonal. Then what? We want to multiply these. And remember the order that it has to be in. It's the E sub 1 inverse, E sub 2 inverse, all the way down to the E sub 5 inverse. So if I multiply all those together, right, I get that. That is my lower triangular matrix. So making sure we do this in order, right? Correct order. It's L and then U. This was the U I found on the previous page, right, where we put it. This was the row echelon form, a row echelon form for matrix A. This is the lower triangular matrix. And you can check and make sure you multiply these together, you get the original one. Okay. Now, that's the idea, but the process, if you think about it, this is quite a tedious process, especially if you have large matrices. When you're multiplying lots of matrices together like that, that takes a lot of computational time. Okay, it's a lot of effort and a lot of work. Okay, and because of that, this method usually is not very efficient if this was the only way you had to proceed. But it turns out, here's the game changer, that there's a quicker way to find the matrix L. A much quicker way for finding that, and that is let's look at the non-zero entries of the matrix L that we obtained here. In other words, the entries on and below the main diagonal. And if you think about how the process worked as we were working through that problem, get back to that page. We started with this entry 2. We did the reciprocal, right? The reciprocal of 2 was a half, right? And notice the entry we left with in that same location is a 2, and that is the reciprocal of our multiplier here, 1/2. Okay, when we introduce that leading 1. Now in this step right here, we after we got the zeros beneath our leading 1, we needed a leading 1 right here. We had a leading 1, but technically you could have multiplied by the reciprocal, which was 1. The reciprocal of 1 is 1. And the reciprocal of 1 is indeed 1 in that same location in our lower triangular matrix. Remember what we had to do here to get rid of that 7? We had to multiply by 1/7. And notice we have a 7 there. So what's happening is in the main diagonal, these entries are coming from the reciprocals of the multipliers that we needed to introduce the leading 1 in that location from the original matrix A. If you look at the entries below the main diagonal, right, well, those correspond to, how did I zero this to get this -3 out? I had to multiply row 3 by 1. My multiplier was 3. And notice we have the opposite, not the reciprocal, but the opposite of the multiplier here, -3. What did we have to do to get the 0 here? We had to multiply by -4. What's the opposite of -4? +4. And then go down to this leading 1, or this 0 here. How did we get this 0? We multiplied row 2, the pivot row, by +3. The multiplier was +3. The opposite of that is -3. And so it turns out that these entries in our lower triangular matrix are the opposites of the multipliers that we use to introduce those leading zeros. And so that's the bookkeeping process. We reduce A to U by Gaussian elimination like we were doing without row interchanges, and we keep track of those multipliers used to introduce the leading 1s and the multipliers used to introduce the zeros below the leading 1s. So in each position along the main diagonal of L, you just place the reciprocal of the multiplier used to introduce the corresponding leading 1, right? Those are just the reciprocals here. Below the main diagonal, we're going to place the negative of the multiplier that was introduced to introduce the corresponding 0. And that's what we do. So we don't need to actually multiply all these matrices together. So let me show you how that would work. Now, that's a lot to take in. Let me just show you this method with another matrix. So I'm going to put this in LU decomposition. I already know my lower triangular matrix has zeros above the main diagonal, so these 6 dots are the things I need to know. Okay, I'm going to take A and I'm going to put it into its row echelon form. So I need a leading 1 here. You say, hey, there's a leading 1 here. We can swap. Remember, we don't want to do row interchanges, right? That we can't. We want to do this process without row interchanges. Okay. And so my first thing is to take 1/2 of row 1, right, and replace row 1 with that. That will introduce that. When I do that, I get the following, right? Multiply everything in row 1 by 1/2. All the other entries in rows 2 and 3 are the same. Okay, but now I know something now about my matrix L, and that is because this entry right here in the first row, first column, tells me the first row, first column entry here. I look at this multiplier, right? And remember, what do? I take the reciprocal. And that is what gets put in up here. Reciprocal of 1/2 is what? 2. Okay. Now the rest I have is 0, 0. Don't know what that is yet. Don't know what that is. 0, and I still don't know what those are. But I do know what that 2 is. I know that entry in the first row, first column. Okay. What's next? And once I get the 1, I want to get zeros beneath it. So the first 0, I'm going to take row 2, and I'm going to add -1 times row 1 to it, right, to get that 0 there. And row 3, I'm going to add 4 times row 1 and replace row 3 with that result. So that does not affect row 1 at all. Row 2, I'm going to do, basically subtracting row 1. 1 minus 1 is 0. 2 minus 1 is 1. 0 minus -2 is +2. And then row 3, 4 times row 1, that gives me a 0 here. And if I do the work, I'm actually going to get a 0 here and a -3 here. Okay. And now, though, I do have 2 new entries in my lower triangular matrix. And that is this entry, right, was found by this multiplier of our pivot row, row 1, but -1. And here, remember, entries, the corresponding entry here, below the line diagonal, we don't want the reciprocal, but the opposite. Remember, that was that bookkeeping approach. We want to find the opposite. The opposite of -1 is +1. Same here with this multiplier 4, which was used to get this entry here in the third row, first column. Again, I want to get the opposite there. And that opposite of 4 is -4. Okay. You've got 3 entries added now. I just need 3 more. Okay. Now, here's the tricky thing. We say, okay, I've got my first column. I want to get the next row, second row, I want to get my leading one. And I have it. You say, I just go on. Just forget about it. But we do have to keep track of it in this bookkeeping method because that's going to give me this entry. So technically, I'm going to say this. I'm going to take the reciprocal of 1, which is 1, multiply row 2 by it, and replace row 2 by it. You say, well, that's dumb. It doesn't do anything to the matrix. It's the same, right? You're indeed correct. It doesn't change anything. But what we're going to do now is to realize that was to get this entry along the main diagonal. So the corresponding lower triangular matrix that we're working on, let's see, this is 1 and -4. This is going to give me the entry in the second row, second column. And again, what is it? When we're doing multipliers to introduce leading ones, it's the reciprocal, not the opposite now, but the reciprocal. Back to the reciprocal. And what's the reciprocal of 1? It is 1. Right. So I know there's a 1 there. So yeah, basically if you have a leading 1 already in the location along the main diagonal, that will correspond to a leading 1 in the corresponding location, or 1, not a leading 1, but a 1 in the lower triangular matrix. Okay, then also I need to get what? Zeros beneath the main, beneath the leading 1. You say, I've got one, nothing to do there. Well, again, with the bookkeeping approach, we want to keep track of what's happening there. So really, I can actually say I want to take row 3, and I want to take 0 times row 2 and replace row 3 with that. I mean, that's the multiplier I would use in the process. Of course, that doesn't change anything. If I multiply a row by 0, I'll just add 0 to the row. It doesn't change anything. But again, this gives me an entry in my lower triangular matrix, namely right here, right? Again, this is an entry beneath the main diagonal, so where we're introducing zeros, and so this goes back to the opposite. And the opposite of 0 is what? -0 is still 0. Okay? So yeah, if there's a 0 already there, we're going to get a 0 on the corresponding location for the lower triangle. So I just, that process, you don't have to write all this out, but I'm just trying to show you how that works. Okay, so you're going to do this real quick, and you can write a program to do this, to fill in this, but the program is going to have to realize if there's a 1 there, you're going to put a 1 there. If there's something other than a 1, you're going to do the corresponding multipliers reciprocal there. And if there's not a 0 here, you're going to do the corresponding multipliers opposite there. One last entry. How do I get a 1 there? Obviously, I'm going to take negative the reciprocal, negative 1/3, row 3, and replace row 3 with that result. And I'm going to get this as my matrix, which is indeed row echelon form. And that row echelon form is going to be our U matrix. And that tells me also what the last entry in my, right? So again, I'm on the main diagonal, so I'm going to take that multiplier, and I'm going to take the reciprocal, remember. That the reciprocal of negative 1/3 is negative 3. And so our final answer, I'm almost out of room down here. So what is our final answer? What's the LU? Now be careful, LU has to be in that order. So when we say it's LU decomposition, notice I got U here and then L, you got to swap, right? L is 2, 1, negative 4, 0, 1, 0, 0, 0, negative 3, and U is 1, 0, 0, 1, 1, 0, negative 2, 2, 1. Sorry, that's kind of small, but that is the actual result. And I didn't have to multiply a bunch of matrices together to get my L matrix. So this bookkeeping approach is the way I want you to do the problems when I ask you to do one. So I'm going to ask you to do a problem like this, and I'm not going to ask you to do it the first way I showed you, but to show it this way, to find the LU decomposition. And then once you have the LU decomposition, use it to solve the system like we did at the beginning of the lecture. Okay. Just one more word to double check. Make sure you multiply these together. There's a lot of room for error. Multiply these together. Make sure you get back to the matrix A. Make sure that's true. Also, I'll just say this: the LU factorization or LU decomposition is not unique. So just because you think of the row echelon form is not unique. So there's many different U's I can get and many different corresponding L's. So there's not a unique answer to this. But this is the one I would like you to do. If you do it this particular way, you will get this LU factorization. Okay, so this is a new method. By the way, this method is used quite a bit in algebraic systems. Some of you might be familiar with MATLAB and some other software that you might have used before. They have often solved their systems using this method. Of course, it has to be a square system again. The cost is in computing this LU factorization. Once you have it, it's easy to solve the system.